On October 24th, 2025, something changed. No explosions, no fiery headlines, just a quiet modification to a small flag in NASA's internal planetary defense dashboard. Status: active monitoring initiated. Object: 3I/Atlas. Code: ICS 1131A interstellar contingency surveillance. Most of the world missed it. But for the few watching closely, researchers, orbital analysts, and planetary defense insiders, that update rang louder than any siren, because this wasn't routine tracking. This was a switch. And once that switch flips, it's never casual. NASA's Planetary Defense Coordination Office, PDCO, is built on layered surveillance. Thousands of near-Earth objects and NEOs pass through monitored zones every year. Most are tagged, tracked, and left alone. But only a handful trigger this level of classification, and almost none of them are interstellar. 3I/Atlas is different, not just because of where it came from, but because of what it's doing. This object, cold, fast, unusually reflective, has been behaving more like a probe than a rock. A slight but consistent deviation in trajectory. Emissions that fluctuate too cleanly to be random. And then the most troubling anomaly of all, the complete absence of a predicted anti-tail, a visual marker that, by all laws of physics, should be there. None of these alone justify full activation, but taken together, they told NASA's Planetary Defense Network one thing: this object doesn't fit the script. The decision wasn't made lightly. It followed 3 days of internal analysis, an emergency orbital mechanics review from JPL, and coordination with the European Space Agency's Near-Earth Object Coordination Center. When the data didn't improve, when the trajectory didn't normalize, the verdict came. Not a warning, not a panic. A hand quietly flipping the toggle from passive to active. Because sometimes the most important changes in the story of humanity don't start with explosions. They start with silence and a line of code. To most people, planetary defense sounds like science fiction, giant lasers, asteroid interceptors, countdown clocks. But inside NASA's real-world protocols, activation is something more subtle and in many ways more sobering. Because when the alert changes to active, it doesn't mean Earth is in immediate danger. It means Earth is paying attention in a way it wasn't before. Let's decode it. NASA's Planetary Defense Coordination Office, PDCO, monitors thousands of near-Earth objects daily. It categorizes them by size, velocity, orbital path, and something called MOID, minimum orbit intersection distance. If an object's MOID drops below a certain threshold, and its characteristics suggest potential unpredictability, a more detailed tier of analysis kicks in. Most objects never rise above Tier 1. 3I/Atlas just jumped to Tier 3. This is what that means. Observation priority rerouted. NASA reallocates telescope time across its deep space and Earth-based networks, including Goldstone, Pan-STARRS, and the Catalina Sky Survey, to prioritize the objects tracking above routine NEOs. Radar lock-in. Deep space radar systems are given instructions to begin narrowband sweeps. These track fine movement and reflectivity data, which can hint at shape, spin, and, critically, non-gravitational behavior. Thermal and spectral monitoring. Instruments like the James Webb Space Telescope in Sophia, in a hybrid capacity, flag the object for irregular emission readings in infrared, ultraviolet, and even hydrogen line spectra. Trajectory modeling acceleration. NASA's JPL Horizon system begins issuing hourly trajectory updates instead of daily ones. This allows scientists to watch for minute deviations, the kind that hint at outgassing, solar influence, or less comfortably, something artificial. Data redundancy and encryption. Once an object is elevated to active status, all data related to it is funneled through secure relays, not to hide it from the public, but to ensure integrity in the analysis. Spoofed data or intentional manipulation becomes a real risk when attention spikes globally. And perhaps most importantly, private defense briefings begin. While public updates remain calm and infrequent, internal memos are sent to U.S. Strategic Command, select congressional offices, and partner agencies. These memos don't declare a threat, but they prepare for possibility, because planetary defense isn't just about response. It's about readiness. The alert for 3 I/Atlas didn't come because it's an impactor. It came because its behavior doesn't fit known physics. And that's where the protocols kick in. We don't wait until a rock is falling. We watch for what might fall before it knows we're watching. That's what activation means. It means the game has changed, and we're officially playing. Most people assume NASA's Planetary Defense Network only activates when something is coming straight at us. A direct hit, a fireball scenario, a rock with Earth's name on it. But 3 I/Atlas flipped that script. Because this time, the alarm wasn't proximity. It was behavior. Planetary defense is governed by algorithms, data-driven, math-heavy, and unforgivingly logical. Every near-Earth objective in NEO is run through orbital predictions, curve fitters, and Monte Carlo simulations. The result is a probability, a forecast. If the risk of impact is statistically insignificant, the alert stays off. But what if the object's behavior breaks the math? That's what happened with 3 I/Atlas. Here's what triggered the escalation. Trajectory drift that couldn't be modeled. Most comets exhibit mild non-gravitational forces. Outgassing creates jets which nudge the body slightly. These can be modeled. 3 I/Atlas, however, show consistent shifts without corresponding brightness increases. No outbursts. No visible mass loss. Yet it was moving subtly, repeatedly, and away from its expected path. Reflectivity modulation. Objects rotate. They flash, they dim, they tumble. But 3 I/Atlas's light curve didn't match a random spin. It pulsed. Regularly. Cleanly. Almost like a beacon. Spectral analysis showed peaks in non-contiguous bands, suggesting either a multi-surface body or something emitting as well as reflecting. Thermal anomalies. NASA's infrared telescopes detected heating patterns inconsistent with solar input. Certain regions of the body remained warmer at night, which shouldn't happen. The heat curve looked more like thermal regulation than passive warming. In nature, there's no precedent for this. A missing anti-tail. At its closest alignment, Earth should have seen a pronounced anti-tail, a perspective illusion caused by dust trailing along the object's orbital path. Atlas had none. The timing, angle, and dust ejection predictions were all perfect, but the signature was gone. Not faint, absent. Orbital precession pattern. The comet's path included a subtle precession, a kind of wobble in the orbital arc that, when simulated backward, didn't point to a smooth gravitational history. Instead, it resembled an object that had been adjusted multiple times across deep space. Individually, each of these anomalies can be hand-waved. Maybe the data's off. Maybe we're seeing things. But together, they tell a different story. One where the danger isn't where the object is headed, but what it might be, because planetary defense isn't just about known threats. It's about unknowns with the power to change the known. And 3 I/Atlas is doing exactly that. Science prides itself on skepticism. Every claim must be tested. Every anomaly needs a second, third, and fourth opinion. But sometimes, the data doesn't wait for consensus. That was the case with 3 I/Atlas. On October 21st, an internal alert was issued at NASA's Jet Propulsion Laboratory. It wasn't a public notice, just a flagged entry in the Orbital Deviation Tracker. Non-gravitational acceleration sustained. Divergence exceeds 3 sigma. That alone isn't shocking. What made it impossible to ignore was what came next. Within 48 hours, 3 separate observatories, Pan-STARRS in Hawaii, the Lowell Observatory in Arizona, and the La Silla Observatory in Chile, reported the same thing. Atlas was not behaving like a comet. Its coma remained compact, unusually so. There was no visible dust fan. Despite confirmed spectral signs of sublimation, the object was outgassing, but nothing was expanding around it. Imagine steam rising, but never spreading. Contained. Suppressed. Then came the reflectivity data. Light from 3 I/Atlas wasn't scattering the way natural surfaces do. Most comets have a regular albedo, patchy, dusty, chaotic. But Atlas reflected light almost symmetrically, with a smooth oscillation that repeated every 4.6 hours. That's not a coincidence. That's a rotation cycle. But more importantly, the signature changed when Atlas passed through Earth's orbital plane. This should have created an anti-tail, dust particles aligned to appear as a forward-pointing tail. That alignment was perfect. The Earth-Sun object angle was ideal. Instruments were ready. And nothing, no spike, no scatter, no anti-tail. That was the tipping point. Because physics doesn't lie. If the geometry is right and the object is dusty, the anti-tail appears. Every time. No exceptions until now. Meanwhile, James Webb logged something even stranger. A narrow-band infrared signature. Not a spike, but a dip, right where thermal re-radiation should have peaked. It was as if the heat wasn't being emitted. It was being redirected or stored. The theory came fast and quiet. What if this isn't a solid body? What if it's a shell? Something hollow, controlled, maybe even engineered? NASA didn't make that claim publicly. But inside defense circles, the phrase structural modulation began appearing in memos. Because the signs weren't just strange. They were systematic, consistent, repeatable, increasing. And for the people watching most closely, one truth became clear. This wasn't a story about impact. It was a story about identity. And they couldn't ignore it any longer. 3I/Atlas has never been invisible. In fact, it's been one of the most watched objects in the sky for the past 2 months. Thousands of images, dozens of spectra, orbit maps, radar sweeps, infrared curves. Its brightness? Clear. Its path? Monitored. Its appearance? Constant. So how could something so public be so misunderstood? Because the truth wasn't in what we saw. It was in what never changed. Since its discovery, Atlas has exhibited a strange optical stability. Most comets flicker and fade, shedding dust and ice as they spiral closer to the sun. Their comas grow, their light curves shift, their tails evolve. But Atlas didn't. Its coma stayed compact. Its tail stayed thin. And its rotation, if that's what it was, remained perfectly timed. No chaos, no jets, no visible fragmentation. For weeks, astronomers called it quiet, stable, predictable. But now, with the benefit of hindsight, that stability looks less like calm and more like intent. What if it wasn't dormant? What if it was deliberate? That's the chilling possibility defense analysts are now modeling. That the thing hiding in plain view wasn't trying to blind us with brightness, but lull us into assumptions. That its greatest camouflage wasn't shadow. It was consistency. In space, chaos is normal. Stability? That's the anomaly. When most people imagine planetary defense, they think of dramatics, rockets, explosions, impact warnings. But real defense isn't loud. It's layered, gradual, and when it activates, the silence deepens. That's what happened with 3I/Atlas. Once the object triggered Tier 3 surveillance on October 24th, NASA's Planetary Defense Coordination Office didn't issue a press release. Instead, it executed Protocol PDC 21B silent escalation. Here's how it works. First, tracking network shift. The Minor Planet Center begins prioritizing astrometric updates every hour. Orbit solutions from JPL are updated in real time, factoring in non-gravitational forces. Private observatories are alerted to increased cadence, higher frequency imaging, broader spectrum analysis. Next, radar lock. The Goldstone Deep Space Complex initiates narrow beam tracking. This isn't just for position. It's to analyze structure, measure spin rate, check for echoes that hint at surface composition or hollowness. If echoes return faster than expected or with lower amplitude, it suggests internal voids or something worse, shielding. Then comes infrared coordination. The James Webb Space Telescope, normally protected from high-priority planetary defense tasks, is flagged for passive monitoring. At the same time, classified satellite assets, U.S. and allied, begin thermal sweeps during Atlas's solar passes. Their mission: detect emissions inconsistent with natural materials. Meanwhile, space agencies around the world are looped in. ESA adjusts its monitoring posture, triggering emergency simulations at the NEOC in Frascati. JAXA deploys Hayabusa-class modeling teams to assess close approach risk to satellite constellations. The Canadian Space Agency launches coordinated Skywatch with INUOSat, one of the only space telescopes designed for fast-moving object tracking. This isn't overkill. It's preparation. Because 3I/Atlas didn't just cross Earth's orbital neighborhood. It crossed a line where natural explanations start to unravel. No, it's not attacking, but it's also not obeying. And in space, with a margin of surprise of 0, even ambiguity becomes actionable. As of today, the object is under 24/7 triangulated observation. Every shift, every flicker, every unexpected emission is logged, shared, and modeled. This is a planetary defense network at full readiness, not with weapons, but with eyes. Because sometimes watching is our first and only line of defense. Science demands proof. It demands repeatability, peer review, cautious wording, and grounded theories. And in 99.9% of cases, that caution protects us from jumping to wild conclusions. But 3I/Atlas has carved out the other 0.1%. Because for the first time in years, astronomers are being forced to consider this. What if the models are wrong? For weeks, planetary scientists have pored over every observable metric, orbital elements, emission curves, reflectivity patterns. And one by one, the assumptions they lean on have begun to buckle. First, they assumed Atlas was a long-period comet. Then, that it was interstellar. Then, that it was natural. Then, that it was passive. But every new data set introduces a new contradiction. How can a comet outgas without a coma? How can it rotate with machine-like precision? How can it show heat redistribution like a vessel, not a rock? The dilemma isn't just technical. It's philosophical. Because if 3I/Atlas is something new, something engineered, controlled, or simply unclassified, then it doesn't just rewrite comet science. It rewrites our role as observers. Are we watching an object or being watched in return? Many researchers are still holding the line, citing data errors, arguing for rare natural mechanisms. And they might be right, but others, quietly, cautiously, have begun to say what was once unspeakable. This doesn't behave like a comet. Not anymore. In the world of orbital mechanics, timing is everything. And with 3I/Atlas, we're entering a narrow, fleeting window where observation becomes not just possible, but critical. Between October 25th and 29th, Atlas will pass through a unique phase angle relative to Earth and the Sun. That geometry creates ideal backlighting conditions, a moment where scattered light from its surface, coma, or internal structure becomes most visible. In simple terms, this is the best shot we'll get. Observatories worldwide are preparing. The James Webb Space Telescope will conduct time-resolved spectroscopy, hunting for subtle spectral shifts that suggest composition changes or engineered modulation. The ESA's solar orbiter is adjusting its telemetry to catch Atlas in high-energy UV as it nears solar perigee, a test to detect sublimation or heat shielding. Even ground-based amateur telescopes are being mobilized, forming a loose global ring of optical trackers. But here's the catch. The window is brief, just 96 hours. After that, Atlas will dip below Earth's orbital plane. Its reflectivity will change, and our line of sight will degrade rapidly. Its outbound trajectory will take it away from the inner solar system, possibly forever. Whatever it is, however it's built, this may be our only chance to study at this range, under this light, with this coordination. And so, the planet watches. Because when a cosmic visitor moves like this, you don't blink, you don't wait. You record every second and hope it tells you something more than just its path. You hope it tells you its purpose. For most of history, humanity looked up at the night sky with wonder, but not worry. Stars were fixed. Comets were rare. The cosmos felt distant. 3I/Atlas changed that. Not because it's dangerous, yet, but because it reminds us how much we still don't know and how late we often realize it. Across the world, telescopes scramble. Defense protocols activate. Scientists argue over models they've trusted for decades. And for the first time since Oumuamua in 2017, the question isn't just what is it? It's, what if it's not what we think? What Atlas has exposed is a deeper vulnerability, not in technology, in assumption that interstellar visitors follow the rules. That celestial motion is predictable, that if it doesn't threaten impact, it doesn't matter. But now that posture is changing. Universities are reevaluating their orbital prediction algorithms. Defense agencies are rewriting protocols for non-impact anomalies. Even private companies, the ones building satellites, telescopes, and lunar outposts, are asking a new question. What else might already be here? Because watching Atlas glide through the system, whisper quiet, perfectly stable, and utterly unlike anything we've tracked before, it's hard not to feel watched back. And that feeling, unsettling, electrifying, is now reshaping how we watch the sky, not just for impactors, but for intention. In the end, 3i/Atlas may pass us by, silently, harmlessly, vanishing back into the black, but it will leave something behind. A shift, not in orbit, in perspective. Because whether it's a comet, a probe, or something in between, Atlas has already accomplished something extraordinary. It's made humanity look up again, not with fear, but with focus. It's shown that even in the most watched sky in human history, mystery still exists, that the universe isn't done surprising us, and that our best defense, our only real defense, is curiosity sharpened by vigilance. We may never know exactly what 3i/Atlas is, but that's not the point. The point is what it forced us to become: more observant, more collaborative, more willing to challenge what we think we know. Because space isn't just vast. It's alive with questions. And if we want to find the answers, we have to keep looking. So if this story moved you, subscribe, stay alert, and keep your eyes on the sky. The next signal could already be inbound.